All right, I've got the power. The last piece of information that we have to learn, other than just the practice that we're going to get in this unit, is we have to learn a little bit about power. So before we define it mathematically, let's talk about power from a conceptual standpoint. Imagining these two scenarios I have here. We have a mass m that we're going to push across the floor with a constant force, F, and then a mass of 4m that we're going to push across the floor with the same force, and we're pushing them the exact same distance. Think about it for a second. Which one of these is harder to do? Is it harder to push the mass m or the mass 4m? And we can actually ignore friction here. Just which one is going to be more challenging to push across the floor? I almost said right there which one of these is more work, but I'll talk about why that's wrong in just a sec. So pause it for a sec, think about it. Okay, great. Glad you had a chance to think about it. You probably came very easily to the decision that the 4m mass would be harder to push across the floor. But again, what's interesting here is that it shouldn't be more work, because work is defined as force times displacement. We're pushing these with the exact same force over the exact same distance, which means the actual amount of physical work is the same for each situation. So again, you're not wrong. The 4m is more challenging, but work obviously doesn't explain why that's true, because we got the exact same answer. Let's change the question a little bit. If I asked you which one would be harder to push across the floor, the 4m mass as a solid piece, or to do the m, but you have to do it 4 times. If you think about that, well, now if we're doing it 4 times, we're still going to be moving the exact same mass, but the difference is we've done it over a greater period of time because we were able to spread that 4m over several trips. So that's what power is. Power is not about how much energy you're expending. It's how much energy you're expending per unit of time. So power is the work you do over a period of time. It's the rate of work being done. Based on that, since we could get this job done in a very large period of time, in a very small period of time, it wouldn't really expend very much power to do that. Whereas this one we're doing more work in the same period of time, so it's harder. I'm sorry, we're doing the same work, but we're doing it in more time, so it would be require more power to do. Yeah, I think that makes sense. Okay, so working our way through this equation, there's an interesting derivation involving power, where we know that work is the same thing as change in energy. So we can substitute that in there. But another way that we could write this is we could say that work is also force times displacement, still over time. And then we could isolate the d over t. So we could say F equals d over t, and then we just get F times V. So this is not on the formula sheet, but it's a common 2 pieces of information they give you on AP exams, and then they ask you questions about the power. They might tell you that you are applying different amounts of force, but the objects are going the same velocity, or same forces but getting different velocities out of it, or something like that. No matter what, remember how to get to this particular solution to help you guys solve these kind of problems. Then I just have a couple quick graphs involving work, energy, and power. One common graph that you'll see is a work versus time graph. And on a work versus time graph, if we do the slope of this graph, that would be the rise, W, over the run, T. And you can see that work over time is a power term. So in this case, the power will be this slope. So that would mean that during the first 2 seconds, we were applying a power of positive 1. I didn't talk about the units yet. The units of power are watts. A watt is really a joule per second, but we have our own special, we just write it with a W for watts. So 1 watt was the power we were putting in. Then you can see that they started doing less work during this period of time. So our rate of change of work was W during that period, negative 1W during that period. And then finally at the end, the amount of power was constant for that last period. We weren't changing what was the energy in our system. So since we weren't changing the energy in our system, we weren't changing, we had zero power taking place. Okay, in this next graph, we have work versus displacement. And the relationship between work and displacement, we have work equals F times D. So if this is our y-axis and this is our x-axis, then this here has to be our slope. So that tells us that during this period here, we have a negative 1 Newton force being applied. During this period here, we have no force being applied, which is why the energy stays constant. And then here, energy is increasing, which means we are applying a force. And the slope is 1, so we know that it was a 1 Newton force for this particular problem. Moving on down, oops, this is kind of in my way. How unfortunate. We have a force versus velocity graph. Now, I just finished telling you that force times velocity is power, and that means this area under the curve represents our power. So we can calculate that during this period here, it's 1/2 times 2 times 2. So we did 2 watts of energy there. Since the force was always positive, we were always adding energy. So the change in energy was a positive change. And then during this period here, again, we have a positive change, 1, 2, 3, 1, 2, 3. Yeah, my math's going to be gross. 3 times 3, so 4.5 watts was added during this period. So we would use the area on that graph to calculate the power. And then finally, I have a force versus displacement graph. And we know that force times displacement is equal to work. So the area under the curve here represents the change in energy, but not the power because we don't know anything about time. So this is what, 10 joules? 10 joules of change there. So those are some common graphs you might see on the AP exam. And make sure you know how to translate from these graphs into useful terms that you can then use to answer the question. Guaranteed, if they had this graph, you'd be supposed to use either the slope or the area to get part of the answer, or maybe the entire answer. So now that you guys all have the power, I hope this helps you guys out. And I'm sorry there was no raps, but you know, this guy doesn't rap, I'm sorry.